right? Is that correct?
2005, yeah.
Yeah. He got his PhD from Cornell in 2000. And so Chris has done a lot of work on the intersection between systems and program verification, formal methods. He's been involved in many of the really famous projects in this space, like Singularity OS, the Verve Verified Operating System, the Ironclad and Iron Fleet projects in Everest, which Nick told us about yesterday. And today he's going to tell us about assembly verification. So welcome, and please go ahead.
Thank you. And as you can see from the first slide here, this is another talk about Project Everest, following on Nick's talk yesterday. And I'm going to focus particularly on how we verify assembly language, and especially how we verify cryptographic implementations in assembly language, implementations of cryptographic primitives. Just to review a little bit about what we're trying to do in Everest, we're trying to verify secure communication channels. And for us, this means, what used to be called SSL, Secure Sockets Layer, and is now called TLS, Transport Layer Security. And it's what you get when you connect to a web server over HTTPS, and it's used for other things like email and so on, as Nick mentioned yesterday. So a kind of a high-level glimpse of what we're aiming for here. So these are snippets from the specifications from TLS 1.2, which is widely used today, and TLS 1.3. Which is just coming out. And these specifications are about 100 pages long. So, kind of large, but still within scope of formal verification. Implementations, so OpenSSL is probably the most widely used and widely known implementation of TLS. And to implement these protocols and these standards here, they take about 40,000 lines of code. So still not too big, within reach, we believe, of formal methods. There's more than just the protocol, though. The protocol saying which messages you send back and forth along this channel. There are underlying cryptographic primitives for symmetric encryption, hashing, and so on. Those are actually a lot more code than the protocol itself. So in OpenSSL, it's about 160,000 lines of code, 160,000 lines of C code, plus another 150,000 lines of handwritten assembly language code, because they want this to be as fast as possible. This is the critical path here, is in the crypto primitives. A lot of that is legacy code. So there was another project called Boring SSL, based on OpenSSL, but without the interesting parts. And they managed to cut this down a little bit, so from 150,000 lines of assembly to 60,000 lines of assembly. And we're not planning on verifying all of that. Some of that still we would consider kind of legacy code that we don't think needs to be the absolute fastest code. But we still think these are reasonable things to target for formal verification here. And so we believe that's also useful to formally verify crypto implementations, because with anything that's 60,000 or 100,000 lines of code, there have been bugs. And so the bugs in these crypto primitives have ranged from the usual stupid heap overflows to just computing the wrong results because they forgot to carry a bit from one word to the other. And so they got the wrong answer in some cases. So we hope to rule out these kind of bugs by applying formal verification to these. And so our goals are to verify basic safety. So the program shouldn't crash, we shouldn't have a buffer overflow and so on. We want more than that, so we want the implementation to compute the right results. So we should write down a specification for these various algorithms that people use. Very symmetric algorithms like AES and Cha-Cha, or hashes like SHA and Poly 1305. and public key algorithms and signatures like RSA, elliptic curve algorithms, and so on. We should be able to write down a concise mathematical definition for each of these and then prove that a complicated optimized implementation actually implements that mathematical specification. And although I won't talk about it in this talk, we also want to avoid side channels, so leaking information through timing and that kind of thing. I won't talk about all of these algorithms here. So some of these algorithms, like the elliptic curve algorithms, have been implemented in and verified in F-star compiling to C as part of the HACL star project. I'm going to focus on the things that we've done in assembly language, and those include for us AES and SHA and Poly 1305. And I'll particularly talk about AES in this talk. And by the way, feel free to interrupt me and ask questions at any time. I'm hoping not to take up the whole 45 minutes here and have time for questions. Let's take a quick look at what one of these cryptographic primitives looks like. So this is kind of a high-level description of Aes Gcm, which is used to encrypt, I think, over 90% of HTTPS traffic today. So this is a very popular and important algorithm. And it's a block algorithm, so if you want to encrypt some plain text, you break up your plain text string of bits into blocks, and I've just shown 3 blocks here. And the specification for AES defines a mathematical function that, given some block of plain text, will and some secret key, will generate a block of ciphertext. So your first attempt at this might be, well, let's just send each block of plain text into this encryption function, and that'll be our ciphertext. That's actually not such a great thing to do. And here's why. If it happens that, say, plaintext block 1 is exactly the same bits as plaintext block 3, and you encrypt them both with the same key, the ciphertext blocks will both be exactly the same too. And that's actually pretty useful information for an attacker if they can see that these blocks are equal to each other. Sometimes they can learn a lot about what you're sending. So we want to mix up the bits a little bit more. And what Aes Gcm does is, instead of encrypting the plain text directly, it encrypts a counter. We just initialize a counter at some arbitrary value that's different for each connection, so say 1,000, and then we encrypt the bits from the number 1001 and 1002 and so on with a secret key. And those encrypted bits are then XORed with the plain text to produce ciphertext blocks. And so that way, even if, say, plain text block 1 and 3 are the same, we're going to be XORing them with different encrypted bits, so the ciphertext blocks will be different. So there's one other thing that I should mention here, which is that if this is all you do, then an attacker who can modify the ciphertext bits can still tamper with this and cause you to decrypt ciphertext into incorrect plain text. So if they've tampered with the ciphertext, you will get tampered plain text, and it would be nice to detect that. So this particular variant of Aes Gcm also sends along a hash of the ciphertext blocks to detect tampering, and it's actually a keyed hash, a message authentication code that mixes in some secret key material to make sure that this hash has actually been produced by somebody with access to the secret. So here's what this hash looks like. We're going to start with some initial hash value and then repeatedly apply some operations that mix in bits from the ciphertext, and we'll just add them in to the initial hash value here, bits from some secret key material, and we'll multiply that in with this running hash here. And then multiplication tends to make the size of your number here bigger, so we want our hash to be small. We'll smash it back down by modding it with some constant that's defined in the algorithm. And we'll just repeat this process for each ciphertext block here. So I haven't yet said what exactly add and multiply and mod mean on blocks full of bits here. And Aes Gcm has a particular definition of add and multiply and mod in mind. It might not be the first thing that springs to mind when you think of this. It's based on polynomials whose coefficients are interpreted base 2. So every coefficient is going to be either 0 or 1, and we'll define operations for add and multiply and mod in terms of these polynomials. So for example, if we add, here we will add 1 times x to the third plus 0 times x to the third to get x to the third. But this x term here, 1 times x plus 1 times x is 2 times x, which is 0 mod 2. And it turns out we don't actually care about the x's, we just care about the coefficients, whether they're 1 or 0. So we can just think of this in terms of bits. And if you think of this in terms of bits, this add is just an XOR. And the blocks of plain text and ciphertext and so on will just be bits here that we do, say, XORs on. So that's add. Multiply is kind of similar. It's just the usual grade school multiplication algorithm where you take the thing on top here and you shift it over for every term that you've got here. So for this, we shift it over 1. For this, we shift it over 2. And then we do the add. And remember, the add is XOR. So again, in terms of bits, this is what it looks like. So an interesting question is, okay, so add had a hardware implementation, a hardware instruction, XOR built in. What is the hardware instruction that corresponds to this operation? It's not regular integer multiply, because we're not doing integer operations here. We're doing this funny polynomial thing. In fact, it's not built in to a lot of architectures, but Intel recently added what they call careless multiply, which corresponds exactly to this. And I'll show you their little blurb here. This is the Intel careless multiplication instruction and its usage for the GCM mode of Aes Gcm. And the name of the instruction is, of course, PCLMULQTQ. I think the P stands for parallel, and it's careless multiply, and the size of the words and so on, but everybody just calls it pickle muckle duck. So anyway, that's what you use for efficient multiplication if you've got the latest Intel processors. And then the very last thing is mod, and I'll kind of briefly go through how you do this here. So if you wanted to take this polynomial on top here, mod x to the third, you can kind of look to integer mod for inspiration. This is sort of analogous to doing, say, something mod 100 in decimal, where you just look at the number here and you chop off all but the rightmost 2 decimal digits. And it's easy to implement mod 100. And if you want to justify that, it's 100 times 24 plus 37, and 37 is the remainder. So doing mod on polynomial, where the polynomial is just a single term there, is very similar. You just chop off all of the terms that are, in this case, x to the third or bigger. Now, the GCM specification is going to ask us to do mod with something a little more interesting than that. So let me just show you real quick what this looks like if, say, we were doing mod x to the third plus 1. And again, we can look to integers for inspiration. If you want to do something mod 99, there's a trick. It turns out you just add the left 2 digits to the right 2 digits. And that is equivalent to the original number mod 99. And if you want to justify it, here's why. You can say this number is 100 times 24 plus 37. And we can rearrange things a little bit and say this is 100 minus 1 times 24, as long as we compensate by adding a 24 in there to cancel this out. And so we're left with 99 times 24 plus the sum of these, which is 61. This trick also works for polynomials. You don't have to read all the math here, but it's exactly the same thing. We're just starting with, instead of 100, we're starting with x to the third, and instead of subtracting 1, well, actually we are subtracting 1 here. And we're compensating by adding this extra x plus 1 here. Mod 2 minus 1 is the same as plus 1. And what we end up with is this thing times something we don't care about plus some remainder, which is our mod. So we managed to do mod with just some bit shifts and bit masks and some addition. And this kind of extends a little bit more if you're willing to do a little multiplication. But we didn't have to do any division, and that's good because division is slow. And if I've learned one thing about people who define these cryptographic primitives, they really, really, really care about being fast. So they've carefully specified these so that you can implement these using very cheap operations like XOR and careless multiply. So that's all I have to say about the underlying crypto. So if there are any questions about that, you can go ahead and ask.
I might as well. Mod is just left shift and add, isn't it? The way you present it, or am I wrong?
It's repeated left shift and add, yeah. But we're actually going to be having fairly large blocks here. So they'll actually be 128-bit blocks, which could potentially be 128 shifts and adds. So if you do that in software, it's pretty slow. If you do it in hardware, it's easy and fast. Yeah, so actually to follow up on that, so what we're going to be multiplying together is 128-bit numbers by 128-bit numbers. We'll get 256-bit numbers. And the magic number that we mod with is x to the 128 plus x to the 7th plus x squared plus x plus 1. That's just what they say. So let me show you how we specify this and implement it in our languages F* and Vale. So this is some F* code here, and it just defines abstract types for these polynomials. And then some operations on the polynomials, like getting the degree of a polynomial. Or down here, I know this is somewhere here. Adding and multiplying, dividing polynomials, so computing like a plus b or a times b and so on. And these are all defined in terms of sequences of Booleans. So a polynomial is just a sequence of Booleans where false is a 0 coefficient and true is a 1 coefficient. And then we go ahead and define operations like add and multiply and so on in the obvious way. So multiply is, as you said, just repeated shifts and adds in this definition. And then once we've got those definitions, we can start to prove lemmas about the properties of these polynomials. Like, for example, multiply distributes over addition. So a plus b, that thing taken times c, is the same as a plus c times, or sorry, a times c plus b times c. Interestingly, mod actually distributes over addition, which is something true for these polynomials and not quite true for integers. So we have a lemma here in F* that we've proven, and it says, as long as you satisfy this precondition that the degree of C is greater than or equal to 0, in other words, C is not the polynomial 0, then A plus B mod C is the same as A mod C plus B mod C. And so we went ahead and proved all of these lemmas in F star based on our definition in terms of sequence of Booleans. So once we have some basic properties about these polynomials, we can start to implement operations on them. And what better language to implement these in than in assembly language, where, for example, we have access to these fancy new instructions like careless multiply. So what I'm showing here is not F star code. This is Vale code, and Vale stands for Verified Assembly Language for Everest. And in Vale, you just write procedures that contain assembly language instructions, and these procedures can have preconditions and postconditions and so on that you can verify, and I'll show how that verification works. So this is the procedure for adding two polynomials, and what the preconditions say is that if we have some ghost values A and B, which are polynomials, and we have some registers, a destination register and a source register, and the destination register and the source register are representations of those polynomials in terms of bits, then the output of this will be the representation of the addition of the polynomials A and B. And the implementation is, not surprisingly, do an XOR, because addition on these polynomials is implemented with XOR. And then, to help the theorem prover along, call a lemma about what we just did, so that to help satisfy the postcondition. So maybe a little more interesting is our procedure for a 128-bit multiply. So Intel provides the PCL MUL QDQ instruction, but that only does a 64 by 64-bit multiply. So we have to put 4 of those together to get a 128 by 128-bit multiply. And so this, we're moving things around in registers, doing a whole series of these multiplies and so on, and then proving that as a postcondition, this is actually a 128-bit multiply. So that's kind of a snapshot of what our code looks like. So are there any questions about that? Yeah.
So where are these instructions specified?
So, all right, might as well show you this. I have the next slide on this. So the very first thing on the slide is the machine model where these instructions are specified. You have to provide this as F star code or Dafny code, or hypothetically lean code, although right now we just support Dafny and F star. And you write down a model that says, this is the type of instructions. An instruction is a move or an add or negate. These are the semantics of the instructions. So given some state and some instruction, what's the next state after executing this instruction? Also, how do you print these instructions when you want to actually run the assembler and generate object files for these? So once you've written down that machine model, you write a Vale interface to the machine in terms of procedures where there's a procedure that you write for each instruction. So there's a procedure for a move instruction, for an add instruction, and you get to pick whatever preconditions and postconditions you want for those, as long as you can prove that the postcondition holds relative to those evaluation semantics. And then in terms of those primitive procedures, you can start to write compound procedures, like here's a procedure that takes in a value in a register RAX and multiplies it by 3 and puts that in the output. So you then give this code to the Vale tool, and it takes, in this case, the triple procedure, produces in this case, just a list of instructions here using this instruction data type, and a proof that the postcondition for this holds, assuming the precondition. And then these values are given to your proof assistant of choice, in this case F star. And then F star says, yes, we believe this proof, or no, try again. And one thing to point out is that the machine model that you specify is part of the trusted computing base. If you get that wrong, it will be some hypothetical architecture that's not ARM or x86, and won't give you guarantees about real machines. And of course, we trust our verification framework. That for this talk, this includes F star and Z3. But the Veil code and the Veil tool are not trusted. So the worst thing that the Veil tool can do is to give you a bad proof that F star rejects. Let's look at what this does in a little more detail here. So when you ask F star to prove something, it's going to turn your request into a verification condition, which is a formula that can be sent to an SMT solver like Z3, and then if this formula is valid, it means that in this case, for example, your postcondition holds, assuming that the precondition held. So in a little more detail, what we'd like this verification condition to look like is something like this. And I'll walk through this verification condition here. So this is going to say, in a context where we're assuming that this initial value of RAX, which I'm calling RAX0, satisfies the precondition. In this case, it's less than 100. Let's prove the following formula, where the different lines in this formula correspond to the different statements in the procedure. So, for example, the move instruction is going to say, let's introduce a new value for the register RBX, which is equal to the value that was in RAX0. This corresponds to moving RX into RBX. For add, it's going to say, you better prove to us that this add doesn't overflow. If you manage to satisfy that, then we'll guarantee that the resulting destination register, in this case RAX, is equal to the sum of the inputs here. And that can be used to help prove the rest of the verification condition. So that corresponds to the last add. And then finally, we want all of this to imply the postcondition here. So this whole thing is valid, then this postcondition will hold, assuming the precondition holds.
I have a question about the thing you said earlier about not having to trust Veil.
Mm-hmm.
Isn't it possible that Veil could mangle your specification so that it's the wrong specification, and then you think you're running code that encrypts something when in fact it's just outputting plain text?
Yes, so the specification should be written in F star, not in Veil, for that reason.
You're still trusting Veil to not mangle the plain text specification when it passes in the word text. That's not much to trust.
No, actually, we don't want to trust that. So what we want to do is write the plain text specification in F star, not in Veil. And we'll still have postconditions in Veil, but if those don't line up with the thing you wrote in F star, then F star will reject the proof. Okay, so if it were this simple, I could end my talk right here. But there's a slight problem here, and it has to do with the level of abstraction that we're actually specifying this machine model at. It's not quite at the level that's written in this verification condition here. It's at a lower level, and it's in terms of states and evaluation operations on states and validity of operands on states and a whole bunch of messy things here. So in our machine model, we'll define a state of the machine to include, say, registers, status flags, memory, and so on. And when we call, say, an add instruction, we have to say a whole bunch of things. We have to say that the machine is in an okay state. We have to say that the operands are valid, meaning like if they're memory operands, they point to a valid memory location. We have to evaluate the operands to make sure that when you add them up, they don't overflow and so on. We have to have framing about which registers change and so on. So this is all just for a single add instruction. So when you actually look at what the verification condition that gets sent to Z3 is, okay, what we want here, I just took a snippet, which is just like, about one line worth of that previous verification condition. That snippet above corresponds to this thing that's actually being sent to Z3. The whole verification condition would take like 4 slides. It's not nearly as nice as we want, and that means that it's actually going to be slower to verify. The bigger the query you give to Z3, the more time it's going to take to verify. And it's largely because we're working at the wrong level of abstraction here. So what can we do? Let's write our own VC generator. Maybe something like this. We'll take in our Vale code, pass it to our own VC generator, generate the thing we want and send it to Z3, and maybe we just ignore F star. And there's some problems with this. Now this is part of the trusted computing base. It said Vale should not be part of the trusted computing base. Here it would be. How do we interact with F star if all our specs and lemmas are written in F star? How do we, or what features would this language have? Can we use F star's features like its type checker and libraries and so on? So I actually don't want to write this in this way. I want to write it in a different way, and I'll show you that after a small philosophical digression. And this has to do with what Nick was talking about the other day, about different styles of theorem proving. So some people have favored a more automated SMT-based approach. Some people have favored a more interactive approach. Actually, I got this quote from 26 years ago saying that there are these 2 classes, automated but impoverished logics, and expressive but not automated logics. And by the way, this system is going to take care of joining the 2. 26 years later, if you look at the papers that are being published, so these are all the verification papers in the major OS conferences in the last 10 years, OSCI and SOSP, they still really fall into 2 camps. All the ones on the left are based on Z3, all the ones on the right are based on Coq or Isabelle Hall. So we haven't yet really merged these worlds together, but the space in between this kind of still fascinates me. So I think we can take advantage of this. So using F star's features for both automation and expressiveness. So in F star, you can write things like these refinements to define a number up to 10 and a number up to 20, and we're going to coerce the number 10 to number 20. And when you try to do this, F star will just kick off a query to the SMT solver and say, SMT solver, please prove that if X is less than 10, it's less than 20. But in addition to kind of that automated approach, F star supports things like higher order logic, tactics, dependent types, and so on. So you can write crazy things like this. Let F be a function that takes a Boolean, and if B is true, return 5, else return true. And you can give this a type, and the type is if B is true, then an integer, else a Boolean. When you apply F to a particular argument, say true here, the type system is going to start evaluating this type here with true plugged in for B, and it's actually going to run a little interpreter to do this and evaluate this to the type int. So to handle dependent types, F star, like other systems like Coq, has an interpreter built into it. We can use this interpreter. So here's how we actually want to write our own verification condition generator. Instead of running this ourselves off to the side of F star, we're going to write the verification condition generator as F star code. Let F star run it using its built-in interpreter and its type system. In addition, we're going to verify that the VC generator is sound using F star's automation. and that will mean that we don't have to include it in our trusted computing base. And since this is all F-star code, we still have interaction with F-star and access to F-star's libraries. So I'll show you how this works in a little more detail here. We have to decide what our inputs and outputs to this VC generator are. So, for example, we could say, okay, the VC generator should take our Veil file as a big string and parse it and generate a VC. But that's going to be hard. So I don't want to do that. Let's let some other tool do the parsing, and this tool will just give us a data type. And this data type is sort of like the data type for assembly language instructions I showed on an earlier slide. But it contains a richer variety of statements, things for making assertions and calling lemmas and manipulating ghost variables and so on. So I won't go into too much detail on that. Let me just go on to what we want the output of the verification condition generator to be. And again, we could just generate a string that gets sent to Z3. But if we're going to prove the soundness of this, I don't want to prove the soundness reasoning about strings. So we could use a data type again. I think that's too hard. So we can just generate an F-star term. This is actually pretty easy because every time we want to say equals in the verification condition, we can say equals in F-star syntax. Every time we want to say implies in the VC, we can use F-stars imply and so on. And when we want to introduce variables like RBX1, RAX2, and so on, we can use F-stars quantifiers to get those in scope and just say for all. So those are going to be our representations. And actually implementing a VC generator with those representations is surprisingly easy. It's just a little recursive function that, so given a representation of a procedure like this here, so this just says, have this sequence of move instructions, add instructions with this lemma call inside, just match on each case here, and for each one, add something to the verification condition. For example, if we're calling a lemma with a particular precondition and postcondition, what we add to the verification condition is you must prove the precondition, and then you get to assume the postcondition in the rest of the verification condition, which is a recursive call. That's all there is to it. It's actually not that hard. Let me just show one more thing here, which is the statement of the soundness of this. As I said, we're going to prove the soundness of this lemma within F-star. I won't show you the proof. I'll just show you the requires and ensures for the soundness lemma. And what this is going to say is, in order to call this lemma, you are required to prove the verification condition for a particular procedure. Represented by this data structure here. If you manage to do that, we will guarantee that whatever predicate you want to be true at the end of the execution is actually true. So if you start in state S0 and S0 evaluates to some final state S1, then this final predicate here, which will be our postcondition, will actually hold on the final state. That's the guarantee made by this soundness lemma. There's one more thing here that I want to throw in, which is an F-star feature called normalize. It's a function that says to the type checker, when you're trying to type check something involving this expression, run the interpreter on this expression, please. And what this will do here is to take your particular procedure, pass it in, and then just recursively evaluate this VC generator until it's generated the entire VC. So when we make a call to this with this particular representation of the procedure, this requires clause will be specialized to this particular procedure. It'll turn into the verification condition for this procedure. And we'll be calling something with a particular requires clause. And when you call something in F star with a requires clause, that requires clause gets sent to the SMT. So this is how our verification condition gets sent to Z3. We didn't have to extend F star or anything with new features here. We just used this normalized feature that was built into it. I'll give the performance measurements, and that'll be the end of my talk. Are there any questions on this? Because I realize this is probably a bit heavy going. But there is a simple message to this, which is this makes things fast. Okay, so the upper graph here shows for Aes Gcm, our Aes Gcm veil code, and our Poly 1305 veil code, how long it used to take us to verify various procedures in milliseconds here, so up to 30 seconds. And in the new version of Veil, where we generate our own verification conditions, how long it takes, which is only up to 10 seconds. So this gives us a pretty good speed up. We also compared it to our older implementation of Veil, which used Dafny. And here the speed up is even more pronounced. So you couldn't fit it in 30 seconds. This dot is actually supposed to be way over there. Relative to what we were doing a year ago in Dafny, we're actually using this technique here to get much faster verification. So that's all I have to say. So like I said, we have verified assembly language implementations with SHA and Poly 1305 and Aes Gcm. And the verification is pretty fast due to F-star's extensibility. So I'm happy to take any questions.
Okay, thank you.
Thank you. I like this presentation. Just a quick question about the size of the VC that you generate. Is it comparable with the previous size, or is it also shorter? The size of the verification condition.
What's the previous size?
Yeah, so you say it's much faster, like up to 3 times faster.
Yeah.
But is the size also of the verification condition 3 times?
It's definitely smaller than 3 times. So basically, this slide here. Sorry. This is not a hypothetical slide. This is real. This is what we're generating in the fast case. This is what the original slow case was. So it's actually much better than a factor of 2.
Okay, other questions? So I was wondering, verification condition generators, like in Boogie, for instance, also track information that you need for error reporting, right, to map verification errors back. Do you do something like that as well?
Yeah, so I didn't show it, but in our real implementation, inside the verification condition that we generate, we insert labels that contain strings that have line number information. And F-star helpfully then reports the errors in terms of those line numbers.
All right. Oh, you have one, okay.
Yeah, very cool talk. Thank you. Can you say something? Maybe you could show the verification condition again, please?
Sure.
The huge.
The huge one, yeah.
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 So can you say something conceptually about somehow where the redundancy is? I mean, why is it possible to write so much better a verification condition this way now? Or why not do it in the first place? Why was it not possible to write something more efficient?
I think there's 2 factors there. So one is that this is at the wrong level of abstraction. So it's in terms of states rather than values. We have to prove that, say, operands that access the state are valid. We have to call functions that get fields out of the state and look up things in maps in the state. And really what we want to be talking about is variables that hold values, not states that have fields and maps and so on inside them. So that's one reason. The other reason is just the F-star verification condition is very general. It's putting things into the context that might be useful for some proofs, but that we actually don't need. In this case, for example, there's this mysterious ghost result 0 that is equal to the result of calling the lemma for add. We don't care about the result of the lemma for add. We care about the postcondition of the lemma for add, not the return value. But F star doesn't know that we don't care about that, so it puts it into the VC anyway.
Okay, thanks.
Other questions? I was wondering, I mean, you have a very ambitious project there with 160,000 lines of assembly code. So what is the main complexity there? Is it to deal with the assembly code, or is it to deal with crypto code?
So I think we have to do a fairly fixed amount of work to reason about the mathematical properties of the crypto primitives. And I would say, like, for the current Aes Gcm implementation, it was probably more work to set up those mathematical properties and do those proofs than it was to prove the assembly language instructions correct. But as we optimize the code more, in particular, use more parallelism, I think that will become the most difficult aspect of it, is just dealing with larger and larger blocks of code that are doing more and more things in parallel, and trying to make the theorem proving scale as the code gets bigger.
All right. So let's thank Chris again.